In the earlier lectures, we have seen that a time varying electric and magnetic field constitute a wave phenomena. Obviously, then this wave requires some power or energy to flow with it. In this lecture, essentially we investigate the power flow associated with an electromagnetic wave. We will do some derivation starting from the basic Maxwell's equation and then ultimately find out how much will be the power flow associated with time varying electric and magnetic fields. Up till now we have investigated a wave which is uniform plane wave, which is a wave propagation in an unbound medium. However, when we are now developing this power flow calculations associated with the electromagnetic waves, we will do the general analysis and not restricted to the uniform plane waves. Of course, at the end of the discussion, we will find out how much is the power flow associated with the uniform plane waves, which we have discussed in the last few lectures. So, whenever we have beginning of analysis in electromagnetics, essentially we go back to the Maxwell's equations and find the answers which is consistent with the Maxwell's equations. Same thing we do here again, that we are asked the question, if you go back to the Maxwell's equations, what answer I get for the power flow associated with the electromagnetic fields. So, in this lecture we are going to do the power flow associated with an electromagnetic wave. Going to the Maxwell's equations and essentially the curl equations, we have in general now that del cross E, that is equal to minus dB by dt. That is, if I assume that the permeability of the medium is not a function of time, I can take mu out and this can be written as minus mu into dH by dt. And the second equation, which will be del cross H, that will be equal to J plus d by dt, that writing out d in terms of the electric field, and again assuming that the permittivity of the medium is not a function of time, this can be written as J plus sigma d E by dt. So, again we start with these two basic equations and then try to investigate the power flow associated with the electric and magnetic fields. So, here essentially we make use of the vector identities and then try to find out meaning to some of the terms which I am going to get in the expansion of the vector identity. So, let me just take the vector identity, which is del dot some A cross C, where A and C are some two arbitrary vectors. This gives me C dot del cross A minus A dot del cross C. So, if I have any two arbitrary vectors A and C, we have this vector identity for these two vectors. Now, what we can do is, let us say this vector A is the electric field and this vector C is the magnetic field. So, substituting for A as E and C as H, essentially the vector identity for these two vectors, the electric field and the magnetic field, can be written as E cross H, that is equal to H dot del cross E minus E dot del cross H. And we can substitute for del cross E from this equation and for del cross H from this equation. So, from here I can get this quantity as H dot, substitute for del cross E from here. So, that is minus mu dH by dt minus E dot, substitute for this will be J plus epsilon dE by dt. Now, I can rewrite for the two arbitrary vectors A and C. Again, if I take a time derivative of this quantity d by dt of some two vectors A dot C, this is nothing but A dot dC by dt plus C dot dA by dt. So, this is true for any two arbitrary vectors A and C. If I take both the vectors same as A vectors, let us say, then I can get d by dt of A dot A, that is equal to A dot dA by dt plus A dot dA by dt. So, that quantity will be nothing but 2 times A dot dA by dt. So, from here essentially we get A dot dA by dt is equal to half into d by dt of A dot A which is nothing but mod of A square. So, this is half d by dt of mod A square. So, we can make use of this relation for simplifying this. So, essentially if I take this mu out, this is h dot dH by dt, that is the quantity which is similar to this. Similarly, if I take this, this will be E dot dE by dt. So, I can substitute from this into this equation and I get the equation as del dot E cross H, that is equal to, from here I am substituting A dot dA by dt, which is half of d by dt mod A square. So, this will become half of d by dt of mod H square. So, this will become minus mu upon 2 d by dt of mod H square. Second term we can have this, which is minus E dot d by dt. So, that will become minus epsilon by 2 d by dt of mod E square, and then we can have finally this term minus E dot j. So, minus E dot j. Now, up till now, since we started with the Maxwell's equations which were point relations, that means these equations are valid at every point in space. This relationship which we have got here is essentially a point relationship. So, any point in the space, essentially this condition is satisfied. So, in general, if I am having a medium which is having a finite conductivity, that gives me the conduction current density J, and if I am having medium which is not varying as a function of time, then in general the electric and magnetic field satisfy these equations. Now, what we can do is we can integrate this quantity over a closed surface or over a volume, and then we will have some meaning associated with these quantities. So, let us say if I integrate this over a volume, I can get this, basically this is a triple integral integrated over a volume. So, del dot E cross H dV, that is equal to the integral, let me take part wise. So, this will be minus integral over V minus mu upon 2 d by dt of mod H square dV minus integral epsilon by 2 d by dt of mod E square dV minus integral E dot j to dV. Again, assuming that this volume is not varying as a function of time, that means the fields are only time varying, but the space is not varying as a function of time, we can interchange this d by dt with the integration. So, we can take this d by dt out of the integration sign, and that same thing I can do here also, and I can apply divergence theorem on this left side to change the volume integral to the surface integral. So, this gives the left side then becomes a surface integral over a closed surface, that will be E cross H dot dA, that is the application of divergence theorem. So, this thing now the volume integral is converted to the surface integral by using divergence theorem, and interchanging the sign for the time derivative and the integral sign, we get minus d by dt of integral mu upon 2 mod H square to dV. This is on surface, which is the closed surface, minus again d by dt integral over V epsilon by 2 mod of E square dV minus integral over V E dot j into dV. I can substitute for j, that is sigma times E. So, this term here, if I look at, and if I substitute for j is equal to sigma times E, this term will become sigma into mod E square. Now, if I look at this quantity and this quantity here, this quantity essentially gives me the density of the magnetic energy stored in the region in this volume. This quantity tells me the electric energy stored in the volume. So, this is basically the electric energy density, this is the magnetic energy density integrated over the volume, gives me the total energy stored in this volume V due to magnetic fields. This is the total energy stored in this volume due to the electric fields. So, d by dt of this quantity essentially gives me the rate of change of the magnetic energy stored in that volume. Similarly, this term gives me the rate of change of the electric energy stored in that volume. Also, the negative sign shows that now this rate of change is negative, that means there is a decrease in the energy as a function of time. So, this quantity essentially tells me the decrease, the rate of decrease of the magnetic energy stored in that volume V. This quantity tells me the rate of decrease of electric energy stored in that volume V. Substituting j equal to sigma E, this quantity essentially tells you what is called the ohmic loss into the medium. So, what we find is that first term here tells me the rate of decrease of magnetic energy in that volume. This quantity tells me the rate of decrease of electric energy in that volume, and this quantity tells me the power loss which is taking place in that volume because of the finite conductivity of the medium. So, if you have a total energy enclosed in a surface, this power loss must be total must be equal to the energy which is essentially leaving in that box. So, if I take this volume V, which is having a corresponding surface area S, since there is no other mechanism of consuming energy, from the conservation of energy essentially we get that this quantity must represent the flow of energy coming from this surface, or rate of flow of the energy coming from this surface. So, from here what essentially we see is that this quantity, the surface integral of E cross H, tells you the net power flow from a closed surface. So, from here this quantity then S represents E cross H dot dA is net power flow from a closed surface. So, we essentially find a very important thing just by doing simple vector manipulations. As we have done, we started with a vector identity, substituted the Maxwell's equations in that vector identity, and from there we find something interesting, that this quantity, the surface integral of E cross H over a closed surface, gives me the net power flow associated with this electric and magnetic field. This statement is called the Poynting theorem. So, the Poynting theorem says, for the electric and magnetic fields, if I take the cross product of that and integrate over a closed surface, that gives me the total power flow from that closed surface. Now, if this is the quantity which is representing the total power flow, we can say that this quantity E cross H is essentially the power density or power flow density on the surface of this closed surface. So, when we integrate this power density over the surface area, that gives me the total power flow from the surface. However, we should keep in mind that saying that since the whole integral gives me the net power flow, that is why this quantity should give me the power density at every point on the surface of the sphere is an arbitrary definition. The Poynting theorem does not say that this quantity is representing the power density or the power flow per unit area at every point on the surface of this volume. What it is telling you is that total power which is coming of this is equal to this quantity. So, saying that this quantity E cross H is a power density and that is true at every point on the surface of the sphere is a arbitrary definition of the power density which we take from here. It so happens in most of the practical situations, this arbitrary definition gives you the power density correctly. However, if you ask rigorously whether knowing this quantity should we say that this is representing power density at every point on the surface of this volume, that statement is not correct. In fact, there may be some very special pathological cases where this argument will fail, that if you have E cross H at some particular point, it may give you a power flow, whereas actually there is no power flow. So, while using this quantity as the power density, one has to be little careful. However, in most of the practical situation, as I mentioned, this arbitrary definition that E cross H gives me the power density, power flow density at particular location, that normally is valid. So, essentially what we get now, an important thing, that we get a quantity what is called a power flow density, and let me call that quantity as some p, which is a vector, and that is equal to E cross H. this quantity P then we call as the Poynting vector for these fields or for this wave. So, this quantity is called the Poynting vector. So, Poynting vector is a very important concept in the electromagnetic waves, because it tells you what is the density of the power flow at a particular point in the space, and also it tells you in which direction the power is flowing, because this quantity is a vector quantity. So, first thing we note here is that if you have the electric and magnetic fields, then the Poynting vector is in a direction perpendicular to both of electric and magnetic field, because we have this cross product. That means this vector P is perpendicular to both of these vectors. So, firstly, if this quantity has to be non-zero, if there is a power flow, then first thing we note here is that E and H should not be parallel to each other. If you have E and H electric and magnetic fields parallel to each other, then the cross product will be identically 0 and there will not be any power flow associated with this. So, only the component of electric and magnetic field which are perpendicular to each other, they contribute to the power flow, and the direction of power flow is perpendicular to both the electric and the magnetic fields. Or said in other words, that to have a power flow in the due to the fields, the E and H must cross each other. Whenever there is a crossing of E and H, there is a possibility of power flow. I am using the word possibility here because this quantity essentially is telling you the so called what is called instantaneous power. So, if I know the value of E and H at some instant of time, at some point in space, I can always find out this cross product at that instant of time, and I will get a number, this quantity P, which will give me the Poynting vector at that instant of time. It is possible that even if there is a P which is finite at some instant of time, there may not be any net power flow over long time periods. That means, if I say in time average sense, there may not be any power flow associated with their system. So, Poynting vector, which we define as E cross H, serves the purpose of defining the power flow, but if I see in a practical system, probably more useful quantity will be the time average value of this Poynting vector, because this Poynting vector, if I take some instant of time, first of all this quantity even may go negative. So, if I say this is telling you power, it may even give me the power which is negative. Of course, when we are dealing with the space, we can say negative power means the direction of the power flow which is changed, but all those complications will come if I use simply the E cross H and get the value of P, because P can go positive, negative. Also, depending upon the time phases between E and H, even this quantity can go as the complex quantity. So, what we do, we essentially try to get the time average value of the Poynting vector, and that is what is more meaningful quantity for finding out whether there is a net flow of power associated with the electric and magnetic fields. As we have seen earlier, in our analysis essentially we are interested only in time harmonic fields. So, we will do the analysis for time harmonic fields only here. So, again we assume that the electric and magnetic fields are varying sinusoidally as a function of time. Only thing, they can have a phase difference between them, the temporal phase difference, and then we can ask a general question: what would be the average power flow or the Poynting vector associated with those electric and magnetic fields? So, let us define now the general time varying fields, which are electric and magnetic fields, which could be varying as a function of the space and time. So, let us say at some point in the space I have the electric field E, which is having some magnitude E0 and is having a variation e to the power j omega t. And let us say it has some phase which is given as phi e, So, this quantity is having some phase which is j times phi e. Similarly, I can have a magnetic field, this is H, which is oriented in some other direction. So, it is having a magnitude H and direction some arbitrary direction, but it is having the same frequency. So, it is e to the power j omega t, but it may have a time phase which could be different. So, this is, let us say this is phi h. What we can do is, we can just take out this vector associated with this as a unit vector and just write down this quantity only as the magnitude of the electric field, the magnitude of the magnetic field. Instantaneous value of the electric and magnetic field, if I take, I can get the instantaneous value values of the fields as your E at some instant of time, that will be the real part of this quantity, and as I mentioned, I can take the unit vector out of this. So, I can keep only the magnitude. So, this will be, let us say, the magnitude which is E 0 e to the power j omega t e to the power j phi e multiplied by the unit vector which is E cap, where E cap gives me the unit vector in the direction of this electric field. Similarly, I can get the instantaneous value of the magnetic field at some time t, which will be the real part of, again I do the same thing, I take the magnitude of this magnetic field e to the power j omega t e to the power j phi h, which is the phase of the magnetic field, multiplied by the unit vector which is the h direction. So, E and H essentially gives me the unit vectors in the direction of the electric and magnetic fields, and phi E and phi H give the phase of the electric field and the magnetic field respectively, and E 0 and E H are now the amplitudes of the electric field at peak amplitudes associated with this. So, if I take real part of this quantity, that gives me the instantaneous value of the electric field and the instantaneous value of the magnetic fields. Once I know this quantity, then I can find out at that instant of time the Poynting vector, which essentially is taking the E cross H of this. So, before that, let me just, if I separate out the real part of this from here, we get the instantaneous value E at t, which will be real part of this quantity. So, that is equal to E 0 cosine of omega t plus phi e multiplied by the unit vector E, and H of the instant t will be H 0 cosine of omega t plus phi h unit vector h. Once we know these vector quantities at that instant of time t, then we can calculate now the Poynting vector. So, that gives me that power density or power flow density at that instant t. So, we can get from here the Poynting vector P, which is E cross H. So, I just take the product of these. So, that is equal to E 0 H 0 cos of omega t plus phi e multiplied by cos of omega t plus phi h multiplied by E cross h. So, this quantity is a scalar quantity and you have the cross product, which essentially is the cross product of the unit vectors. I can simplify this. So, this gives me essentially E 0 h 0 upon 2 cos of phi E minus phi h plus cos of 2 omega t plus phi E plus phi h multiplied by E cross h. Now, this is the instantaneous value of the Poynting vector, and as we mentioned, we are now interested in finding out what is the average value of the power density, or what is the average value of this Poynting vector. So, we can take a time average of this over a period of the signal. So, if I integrate this power density over one period or one cycle, essentially we get the average power density associated with this, but over that one period this quantity will go to 0. So, essentially this is corresponding to a waveform which is having a frequency of 2f, or the angular frequency 2 omega. So, over a period corresponding to omega, this quantity will identically go to 0. So, if I take the time average of this quantity, which is P average, which is 1 upon T integral 0 to T P dt, where T is the time period associated with this angular frequency omega. So, T is equal to 2 pi divided by omega. Then I get the average Poynting vector, and in that this quantity will essentially go to 0. So, I get the average value of the Poynting vector P average, that is equal to 1 upon T integral E 0 h 0 upon 2 0 to T cos of phi E minus phi h dt E cross h. So, the average Poynting vector now is the average value of this quantity, and you have a cross product of the unit vectors of the electric and magnetic fields. Now, this quantity is not a function of time, this is constant. So, this can be taken out. So, the integral will be 1 upon T integral 0 to T dt, which is nothing but equal to 1. So, this P average now we have is E 0 h 0 upon 2 cos of phi E minus phi h, and this cross product of the unit vectors E and H. We can do little more algebraic manipulation to write again back the electric and magnetic field in the vector form, in the phasor form. So, what we can do is this quantity now can be written as half of real part of E 0 e to the power j omega t plus j phi e and take the vector with this. So, that will be E, this is one quantity, cross h 0 e to the power minus j omega t minus j phi h to h vector. So, what we have done? We added this quantity e to the power j omega t and e to the power minus j omega t in the expression. So, if you see here, this will be E 0 into H 0, these are scalar quantities, you will have cross product of E and H, which is this, and if I take real part of this quantity e to the power j phi multiplied by e to the power minus j phi h, that will give me the cos of phi minus phi h. Now, the same thing, if I take this negative sign here, this quantity is the scalar quantity. So, you can write this also like that, real part of this quantity, which is E 0 e to the power j omega t plus j phi e unit vector E cross h 0 e to the power plus j omega t plus j phi h conjugate of this quantity. So, the conjugate of this quantity will be, this quantity is a scalar quantity, real quantity. So, the phase complex quantity is only this e to the power minus j omega t minus j phi h. So, if I take a conjugate of this, essentially this represents this quantity. But this quantity is the original magnetic field which we had defined in the vector form. Similarly, this is the quantity is the original electric field which we defined in the vector form. So, essentially we have this quantity here. The electric field is E 0 e to the power j omega t plus j phi e multiplied by unit vector. Same is true for the magnetic field here. So, this quantity is nothing but electric field and this is vector magnetic field. So, this is half real part of E cross H conjugate, that is the average Poynting vector. So, if I know the electric and magnetic fields in the complex form, that means the electric and magnetic field may not be in time phase all the time, then in general we can just calculate this cross product of E cross H conjugate, and real part of that, the half factor essentially is because of the RMS value as we get in the electrical signals. So, since the signals are time varying sinusoidally, essentially this is a factor which is the RMS factor. So, this gives me now the average power flow which will be associated with that electromagnetic wave. Now, this quantity is a real quantity as we are taking a real function of this. So, all those problems which we had with the instantaneous power flow, which could either become complex depending upon the phase difference between them, and on all those have been now taken care of, and also it tells me now the overall power flow which will be associated with these fields at their particular location. So, it is possible at a particular location the instantaneous Poynting vector might be negative or positive, but when you calculate the average power Poynting vector, that will be always positive and that will give me the net power flow which will be associated with those electric and magnetic fields. So, this is the concept which is very regularly used in finding out the average power flow associated with an electromagnetic wave. So, again, to have the average power flow, there are two things now essential. One is that the electric and magnetic field must have a component perpendicular to each other, then and then only you will have a cross product which is non-zero, and at the same time the electric and magnetic field should not be in time quadrature. That means the phase difference between the electric and magnetic field should not be 90 degrees, because if it is 90 degrees then this real part of this quantity will be 0, and then you will not have any real power flow associated with that point. So, in general it is possible, if you take the electric and magnetic fields, you will have the complex power. The real part of that quantity gives me the net power flow at that location, but the imaginary part of that quantity E cross H conjugate, that gives me the power which is oscillating around that point. So, at some instant of point the power might be going in a certain direction. If you see, after some time the power will be essentially coming back in the same direction. So, the imaginary part of E cross H conjugate, that gives me some kind of a oscillating power which we call as a reactive power, whereas the real part of E cross H conjugate gives me the net power flow, or the what we call the resistive power flow at that particular location. So, this concept of Poynting vector and the average Poynting vector is a very important concept, because by using this concept we can calculate the net power flow at a particular location. One can then apply this concept to the case which we already discussed, that is the uniform plane wave. So, we can ask, if you are having a uniform plane wave, then how much power density the uniform plane wave carries when it travels in the medium. So, we have seen for uniform plane waves, first of all the electric and magnetic fields are perpendicular to each other. So, if I take a uniform plane wave, then the electric field, the magnetic fields are perpendicular to each other, and then this is electric field, let us say E, this is the magnetic field which is H, and the power will be flowing in this direction, which is this, which is the cross product of these two. So, this is the direction of the Poynting vector P average. Again we can apply the right hand rule to find out whether the power will be flowing in this direction or will be flowing in this direction. So, since we are taking the cross product of E and H, again we point the fingers in the direction from E to H, and the thumb should give me the direction of the cross product, which is the direction of this. This direction is same as the direction of the wave propagation also, because we have seen when we talked about uniform plane wave that E, H and the direction of wave propagation essentially form the 3 coordinate axis in the same sequence. That means, if I go from E to H, if my fingers point from E to H, the thumb should go to the direction of the wave propagation. So, we correctly get the direction of the average Poynting vector, which is same as the direction of the wave propagation. That is one. Secondly, if I say now the electric field is some magnitude E0 and is having a now the phase variation which is e to the power minus j beta. Let us say the wave is travelling in direction z. So, this is the direction which is z direction. So, e to the power minus j beta z, and E could be oriented, let us say, in x direction. So, then H will be oriented in y direction. So, I can say this is, let us say, is oriented in x. Then the magnetic field H will be oriented in y direction. So, it has a magnitude S0, phase minus j beta z, and its orientation is the y direction. So, the average Poynting vector associated with this P average, that is equal to or half real part of E cross H conjugate. Now, the cross product of x and y will give me direction z. So, this average Poynting vector is in z direction. So, this is half of real part of this conjugate this. So, essentially that will become E0 to H0. So, this will give me E0 H0 in the direction z. If I assume in general this quantity could be complex quantities, I can put even the still the conjugate sign at this. So, for a uniform plane wave, the average Poynting vector will be half of E0 H0 conjugate, and the direction of this will be Z. If we say that the electric field was oriented in x direction and the magnetic field was oriented in y direction. Now we can take specific cases for the unbound medium in which the uniform plane wave is propagating. We can take first a medium which is dielectric medium. Now for a dielectric medium, or in general if I take an unbound medium, first of all we know there is a relationship between these two quantities E and H, that is the magnitude of the electric and magnetic fields are related through what is called the intrinsic impedance of the medium. So I also have for a uniform plane wave a relation that electric and magnetic field that is equal to eta, which is intrinsic impedance. So I can substitute for the magnetic field from here, that will be E upon eta, or I can substitute for electric field which is H times eta. So I get the average Poynting vector E average, that is equal to half of E0, H0 will be E by eta, so this will be E0 by eta conjugate Z direction, or if I write in terms of the magnetic field, this will be also half eta into H0 conjugate into Z. Now E0 conjugate is mod E naught square, so this is equal to half mod E naught square upon eta conjugate, or equal to, of course if I am putting a conjugate here I must put a real part of that. So this is a real part of this quantity. So same thing you have to put here, this is a real part, this is real part, so this is again a real part of this, and will be half into real part of eta to mod of H naught square into Z. So from here essentially we can find out what is the average power flow associated with the uniform electromagnetic wave in an unbound medium. Now if I take a medium which is a dielectric medium, a ideal dielectric medium, that means there is no conductivity in this medium, for which we know that eta is square root of mu upon epsilon. So this quantity is a real quantity for a ideal dielectric medium. So this quantity essentially the eta conjugate, since this is a real quantity, is same as eta. So in this case the average power density E average will be equal to half of mod E naught square by eta, that will also be equal to half of eta into mod H naught square. So in a dielectric medium, if I know the magnitude of the electric field, or this is the peak amplitude of the electric field, and I know the permittivity and permeability of the medium, then I can find out this quantity intrinsic impedance of the medium, this quantity is real. So just by knowing the amplitude of the electric field I can get the power flow density associated with this uniform plane wave. Of course if in general this medium is having a conductivity which is neither 0 nor very large, which is like a conductor, then we have to really go through this expression to find out what is the net power flow associated with it. However, we can take an extreme case, and that is if you have a good conductor, then we know that the intrinsic impedance of this medium is approximately equal to square root of omega mu divided by 2 sigma plus j square root omega mu by 2 sigma. This we have already seen. So, if I take now this intrinsic impedance and substitute in this expression here, then I can get the average power density P average, that will be equal to half mod E naught square root of sigma upon 2 omega mu. So, essentially by using the concept of the average Poynting vector, we can find out the power flow in any medium and at any particular location in the space. In case of dielectric, the calculation is very straightforward because the intrinsic impedance of the medium is real, whereas when we go to the medium which is like a good conductor, or in general medium where conductivity is finite, then one has to go to the more general expression for finding out the average power flow associated with the electric and magnetic fields.